Here are more rate problems today, and we've got two different types for part number one. And the first one's an opposite direction problem. So this is a key word here. Whenever I see the words opposite direction, and I know I'm dealing with distance, rate, and time, that tells me what type of problem or how I'm going to end up setting it up. So let's read what it says. Two cars leave town at the same time going in opposite directions. So to show you a picture, this is what it looks like. One car is maybe going slower. One travels at 35 kilometers an hour. The other car, let's say, goes a little bit faster. And it went a little further because they left at the same time. Since it goes a little faster, again, that line's a little further. And they're asking how long will it be until they are 200 kilometers apart. So the distance from this point to this point is going to eventually be 200 kilometers. Now notice, neither of these cars travels the full 200, but together they add to make 200. We're going to use that concept when we're solving this. So let's go ahead and set up our two equations. We've got distance equals rate times by time. So my distance, again, I've got car number 1 and I've got car number 2. My distance for car number 1, we don't know. We don't know either distance, but we do know together they went 200 kilometers. So we need to assign one of them a distance, and so D for distance. So let's call the one that went slower D. He had the shorter line there, so we'll go with that one as our D. So I'll write down D for car number 1, and now his rate was 35 kilometers per hour. Now, they left at the same time. They don't give us a time, but we know it's the same time. Since we don't know what that is, let's just go with T. So we'll go with T right there. So we've got our first equation. D equals 35T. Let's set up the next one. The next one, the D part, is a little different. Now, we don't want to use a different variable. See, I already have two unknowns, D and T. I know their distances are not the same because the one that was going faster went further. So I can write an expression for this distance, and the expression is going to go this way. It's going to be the total 200 minus D. Because if I took away this portion right here, if I took this away, I took it away, meaning subtracted it, I would subtract it from the total distance, leaving me with the shorter distance. And that's how I'm going to write it. 200 minus D. So I got to write that in for the distance for car number 2. 200 minus D. And this all equals its rate, and its rate was 40. So we'll write down 40, and the T is still the time. There it is. We've got our second equation. And this is a great substitution problem because we've got a variable by itself. D equals 35T. So let's just take that 35T and let's put that in place of the equation below, in for D. And so what we'll do is rewrite it. So 200 minus D, but we're putting 35T in place of that. And then this all equals 40T. And so from there, we go ahead and do an opposite operation to get 35T to the other side. So I'm going to add it to both sides. And once I do that, I have 75T equals 200. And so this is just going to give me the time. And looks like that's what I want. I want to know the time it takes for them to be at that distance of 200 kilometers apart. So I'll divide by the 75 on both sides. And in this case, it doesn't quite go in there evenly, so we're going to end up having to reduce it. Now, when I reduce something like this, I see that both of them have a factor of 25. And I know that because they end in either double zeros or, in this case, 75. So I'm going to reduce it by dividing by 25. And I see that 25 cents goes into $2 8 times. So that makes the reducing quite fast. This would be 3. 25 goes into 75 3 times. So there it is. Now it's easy to do the division. So just 3 into 8. So that would be 2. and 2/3 hours. And that would be our answer. H equals 2 2/3, or time equals 2 2/3, I guess I should have said. Well, let's take a look at what we did again as we were trying to solve that, because this is a big concept, and we're going to be doing a different type. We're going to be doing a same direction problem next. So opposite directions, we are going in opposite ways, and they're going to give us the total distance apart. Whenever we're given a total, always take the total away from the part. And so it's always total minus the part. And that's the big difference here with an opposite direction and a same direction problem. So let's take a look at the next one. This is a same direction problem. So two cars leave at the same time, again, going in the same direction. So two different types of problems. So let's draw the picture here. Here are the two cars. One's going to be going slower, one's going to be going faster. And so one goes 30 miles an hour, the other 46. How many hours until they're 72 miles apart? So the distance from the slower car to the faster car will eventually be 72 miles. So notice, the slow car might not have traveled 72 miles. We don't know how far it did travel. The faster car definitely drove 72 miles plus an additional amount. And so we're going to use that concept when we're trying to write our equation. So let's go ahead and write it. Well, let's do a slow car and a fast car this time. Slow and fast. And we'll write our equation up here. D equals R times by T. So the distance for the slow car, well, we don't know what that is, so let's call it D. Let's just put in D right there. So distance was D. The rate we do know. It said 30 kilometers per hour. So I could put 30 in there. And then T. We don't know the time, but we do know they left at the same time. So that's when we use a variable, T. Alright, now the next car, the fast car. Notice the fast car, it's different than the opposite direction problem, because opposite directions we were given a total. Neither car had driven that 200. But here, the same direction problem, the faster car has gone the distance the slower car went, so D, and means plus, it's gone also the distance of that they're apart, 72 kilometers, or 72 miles in this case. So that expression is going to be D plus 72. So that's the difference between an opposite direction and a same direction problem, is the way the expression is set up. Otherwise, it's pretty much the same. It equals the rate, 46, times by the time, well, they left at the same time. So we've got our two equations. We can go ahead and solve. So the way we'll solve is just by using substitution again. Take that 30t and let's put it in for D, the equation below. So now I've got 30t plus 72 equals 46t. And so I'm just going to do a opposite operation. Subtract that 30 from both sides. And when I do that, I'm left with a 72 equals 16t. Divide by the 16, and we'll have our answer. So in this case, we end up with t equaling, and that's going to be a fraction. It doesn't quite go in there evenly. So let me go ahead and do some reducing here. I'm going to take out an 8. I know 8 goes into these two numbers, so I'll go ahead and divide this by 8 and divide this by 8. And so that makes a 9 over 2, and that makes the reducing of dividing a lot easier. So 4.5 hours is the time it ended up taking the cars to be 72 miles apart. So notice the difference. Oftentimes you're given a same direction or an opposite direction problem. Notice that on same direction, the slower one is the variable I use, and then for the faster one, it's just that variable plus the distance apart. Opposite directions, you're given a total. Whenever you're given a total, you assign one of a variable. The other is going to be the total minus that variable. So those are opposite direction problems. Then we've got one other problem that deals with a wind speed again, and so we'll see that in part 2.